Good afternoon, everyone. Thank you for joining us for today's webinar. My name is Neil Foley, and I'm the Applications Engineer at RIZE. Today, I'm going to be discussing assemblies of 3D printed RIZE parts and some best practices for designing such assemblies. All right, so here is an overview of what I'll be covering regarding best practices for designing assemblies with RIZE. First, I'll discuss the basics of designing components for assemblies of RIZE parts. Then we'll expand to include external hardware. And then I'll discuss our augmented polymer deposition process and a few unique capabilities that allow RIZE printers to produce some pre-assembled designs and special joints. Finally, we'll look at a few use cases of RIZE assemblies. So there are a few features of RIZE parts that make them useful as assembly components. The high strength of our material. So the high strength of our material, Rhizium-1, means that the parts will be functional and durable. The precision of our printing process ensures that corresponding components will be replaceable and interchangeable. And the marking ink capability of our APD process also offers a few useful functions for assemblies, including color coding the components and annotating surfaces with assembly instructions or markings for guidance. So shown here are a few assemblies produced entirely from components printed with RIZE. First is a gear assembly driven by a winch handle. It has several parts that are assembled entirely from parts printed from RIZE. And then the second part is a hinge joint assembly with components that have been color coded. So this part was printed on our RIZE machine, which is still being developed. So when designing an assembly composed of RIZE parts, there are several things to consider depending on how the components of your assembly are joined. If an assembly involves hinges or pivot joints, there is often a cylindrical axle or pin that needs to rotate within a barrel. So to ensure that the circular surfaces will not interfere, it's generally best to leave a radial gap of about 0.3 millimeters for a loose fit between the axle and barrel. That's what I usually use, the 0.3 millimeter gap. It can depend a lot on the geometry of the parts that you're producing, especially the total diameter of the axle and barrel. So typically, it's best to experiment with the size that you're going to be printing before you create the final part. So this can be affected by the orientation of the axle, particularly if the chosen orientation produces a seam. So it will depend on the particular geometry of your components. Another common joint is a sliding joint, wherein a track or protrusion from one part fits into and slides along a corresponding feature on another part. This type of joint should similarly use surface gaps of about 0.3 millimeters, and it's often best to fillet sharp corners to prevent them from interfering. This is especially the case for corners that are going to be up close to the part that they're sliding alongside. In some cases, the corner of a part will extend a little bit further than the walls on the sides of it. So another approach that's useful for assembling a large or complex part with rigid connections among its components is to create jigsaw-like or toothed interfaces that can be glued together. So this is useful for when you are trying to create a large part that doesn't necessarily fit entirely onto the build plate, or perhaps it's very complex and it's not practical to print the whole thing in one job. So you'll print it in separate pieces, and then you can glue the pieces together once you have a strong enough joint to hold them. So our material Rizium 1 is quite chemically resistant and does not bond well to most adhesives, but the chemical D-limonene can be used to successfully glue Rizium parts together in this way. Now, the last joint I'll discuss here is the fitted surface, by which I mean a surface created as an offset of another that fits to it exactly. Fitted surfaces are useful for jigs that hold parts with complex surfaces, but they can also be useful in assemblies, and additive manufacturing allows complex or curved surfaces to be created more easily than most subtractive manufacturing methods. When creating a fitted surface between two parts printed with RIZE, it is typically best to use an offset of about 0.2 millimeters for a snug fit. That's the approach I typically use. So there are a few pictures here. At the top is a sliding joint, and this particular sliding joint was printed all at once, and there was a bit of support material between the axle and the barrel, and that could be broken off easily enough, and then the axle slides back and forth through the slot. Then the part on the bottom is our multi-tool with a jig that has a fitted surface. So the way I created this was to take the surface of the multi-tool in CAD software and offset it by 0.2 millimeters, and then basically cut that portion out of the shape of the jig, and that allows the multi-tool to fit into it very snugly. All right, now in addition to constructing assemblies from RIZE parts, you can also, of course, join RIZE components into assemblies using or including other hardware. This is useful for all sorts of things, including replacing broken parts of manufacturing assemblies or printing fixtures to attach assembly components together, creating functional prototypes, and even producing end-use service parts. The tolerances for most applications with external hardware can be treated the same as for assemblies of RIZE parts only, with a few exceptions. So some common hardware components that are used with RIZE parts include threaded inserts, drill bushings, and various fasteners. Shown here are a few assemblies composed of both RIZE parts and external parts. The first is a functional prototype for a fan assembly. It was used to test the design for the RIZE 1 printer's extruder assembly before being manufactured at scale. So initially we tested this design in Rizium with the final fans attached to it and with bolts connecting it to the extruder assembly. And once we verified that, we were able to then convert the process to injection molding. So then the second part shown is a simple handle assembly for a sheet of sandpaper. And it's just 4 pieces, one at the bottom that you attach the sandpaper to, and then the 3 at the top clamp into the bottom, and they secure the sandpaper in place. And then the last part is a drill guide jig assembly with both drill bushing inserts and levers attached. So that one has a bit of a variety of hardware used in that assembly. So here I'm going to take a moment to talk about what RIZE does differently that provides some special capabilities. So our technology is called augmented polymer deposition, and it offers a wide variety of applications. So it involves the simultaneous extrusion of our own compound of medical engineering grade thermoplastic and jetting of special inks. So first, thermoplastic is extruded, forming the support structure. Next, release ink is jetted between the support and the first layer of the model structure, which eases the removal of the supports. Then, more thermoplastic is extruded, forming the model. And finally, some special inks are jetted between the layers of thermoplastic to control material properties by voxel. So, in addition to assembling printed parts together or with other components, you can also print assemblies as a single part with moving pieces. And the ability to jet release ink and other functional inks allows us to get some useful effects out of this. So this strategy offers a few benefits in balance with some costs. It typically takes more time to design a working assembly this way because printing the components pre-assembled involves adding several constraints to the design process. So this front loads the labor required into the design phase, where extra complexity is added to fit components into one single print. Now, the benefit of using this strategy is that it reduces the post-processing required for each print because RIZE's APD technology already enables rapid and easy support removal. But printing assemblies pre-made eliminates the need for post-process assembly. So by printing the parts all together, you eliminate the need for assembling them after they've finished printing. So this is primarily useful for assemblies that will be produced at high volume, as each print that you produce saves time from post-processing. So when you're deciding whether or not to produce an assembly in this way, you'll have to think about the balance between how much extra time will need to be spent in the design phase versus how much time you'll be able to save in the post-processing phase. And that will essentially be a function of how many instances of the assembly that you're going to print. So some examples of this approach are shown here. There's the classic ball bearing, which many 3D printers have produced over the years. With RIZE's precision and ease of support removal, this can also be converted into the fidget spinner toy shown with much smaller pieces. It would be very tedious to insert each ball separately, but printing pre-assembled makes it much faster and easier. There's also a small clamp shown and a gearbox cross-section. On the next slide, I'll discuss some of the different strategies for achieving this effect. So there are two main ways of printing pre-made assemblies. The first strategy, the one that most 3D printers would use, is to build all components up from the base of the build. This is how the ball bearing and clamp from the previous slide were designed. Each component is attached to or supported by the build plate, and the components are kept separate during the print. This is a useful method, but it also limits the range of assemblies that can be produced with these requirements. The second strategy, specific to RIZE printers, is to build components wherever they are needed, but separate each component with a layer of support. Because our APD technology allows us to jet release ink between model and support layers, such components can be broken free from the interface. This strategy opens the way for a wide variety of new joints and connections among assembly components, such as hinges, pivots, and ball joints. Printing parts in this way requires careful planning to achieve success. So if you wish to use this method, there are several things you'll have to pay attention to. The first is the interface area. So you'll need to reduce the surface area that connects each component to the support layers to ensure it will be able to break free. You'll also need to leave gaps for the components to move around in and ensure that those gaps don't get filled with support layers. And one effective way of doing this is to use self-supporting build angles. So there are a few parts shown here. Two of them use a similar strategy where there is a part built on top of another and it rotates within that part. And when these are being printed, they are connected at the base of the inner part, and there is a layer or two of support material that separates the bottom of one part from the top of the other. And what this allows you to do is, once these parts are printed, you can take the parts and rotate the inner pieces, and it will crack the interface of support material with release ink on it, and that will allow you to have a rotating joint, and the parts will still be fully connected to each other, and that you can't pull them apart. So this allows you to create assemblies that couldn't otherwise be put together, because once you have these parts built together, you can't get them apart unless you break them. So the ball joint is fairly similar. The outer part of the joint was printed on the bottom with the inner ball printed on top, and there was a gap between each sphere with a bit of support material separating the bottom of the ball from the top of the bowl. So once the print was finished, you can simply crack the two axes and the ball will separate from the support material and you'll have a working joint. So there's a wide variety of ways of using this strategy. There's some challenges to each way that you use it. So I would say if you are interested in using this type of joint in one of your assemblies, probably to begin with, you should probably reach out to one of us at RIZE to help get you started on it. So now I'm going to discuss a few use cases. So here is one use case for using RIZE for assemblies. This is a wooden toy puzzle. The puzzle comes apart into 12 different pieces and it can be tricky to reassemble them. And that's the game of it, trying to put the pieces back together. So this is similar to a manufactured assembly that has many distinct pieces and is challenging to assemble without detailed instructions. So RIZE's marking ink technology allows you to add instructions and other annotations to the surface of assembly components, which can make complex assemblies much easier to build. The part shown on the right is an example of this. Each wooden component of the puzzle could be marked with a number identifying its step in the assembly, along with annotations referencing other components. Now, of course, this approach entirely defeats the purpose of the wooden puzzle toy, but it can be useful when applied to various assemblies, from prototypes to replacement to complex jigs and fixtures that would be challenging to assemble without instructions. And here is a second use case. This is the cross-section of a gear that was shown on a previous slide. So this gear assembly has 4 components that are all printed in one print job. And then once the print is completed, you can turn the handle at the top and it will separate the interfaces for all of the rotating joints that are built into it. And once you've cracked all of the joints, then you have a working gear assembly from either handle that you use. So this is quite a complex part, and a lot of time had to go into designing it. However, because it is printed in a single piece, what this allows you to do is print each gearbox assembly with no assembly required after it finishes printing. So if you're using this part for producing gearboxes at scale, then it would reduce a lot of time that would have been spent assembling the various components once the print finishes. All right, so That's all I have now. Thank you again for attending our webinar. And as always, you can reach us at applications@rize3d.com.